Welcome to a new video about analog filter design. In this example, we will discuss the high-pass filter having a buffered circuit configuration. You see here the two buffers. More details will be follow. And we will see how we can determine the transfer function and use that to determine the design equations for our example. Of course, we will see everything step by step in our calculations and verify these in SPICE simulations. Before we jump to our design example, let's first discuss the buffered high-pass filter circuit. You see here the C1 and R1, which is our first stage. Again, here the buffered version. And then we have here C2 and R2, which is again our high-pass filter. So these two configurations with the two RC circuits will create a second order high-pass filter. And we have also the two buffers using an operational amplifier. The transfer function for this circuit is shown here. We see here the S squared again in the numerator, which is the characteristic of a high-pass filter. And the second order expression here where you see also the component values R1, R2 and C1 and C2. We can make the design a little bit easy by selecting the capacitors equal to each other. So we can say C1 is equal to C2. So that makes and define this, for example, C, and that can reduce the number of nodes and also our design steps. So that will be then S squared over S squared plus 1 over the R2 C. And this will be then 1 over R1 times R2 times C squared because this is C1 times C2. The second order high-pass filter standard form transfer function is given by this expression. You see here the K, the omega n and the Q. You have seen this also in the other videos. Let's briefly again discuss what they are. The K is our passband gain. For a high-pass filter, that means actually the gain at high frequencies. The Q is the quality factor, which determines the shape and the sharpness of your filter. And the omega n is our natural frequency in radians per second, which is related to the resonant frequency. We will see the details shortly. Now, if you now compare the terms of this transfer function here and the transfer function in the standard form, we recognize directly this 1 over R1 times R2 times C1 times C2 is this omega n squared. That's shown here. The K must be 1 because this is 1 times S squared, so this is then 1. So the gain is always 1, so it is unity. And we see here the omega n over Q is this 1 over R2 times C2. That's actually shown here. Now from this, we can now develop the design equations. Now first we can take the square root of the left and right hand side of this equation. So we get here the natural frequency is the 1 over the square root of the product of the four components. That can be also written like so if you have the C1 is equal to C2 condition, which is the equal capacitor method. The Q can be written like so. We use this formula. You say Q times 1 cross multiplication and then is equal to omega n times R2 C2. Now we know omega n, which is shown here, so we can put it here of that in the general form, and R2 times C2 will be then in the numerator, and you will now get in the form the square root of the R2 times C2 over R1 times C1. Now if you again use the equal capacitor method, you can then divide out the capacitor because these are equal to each other, so you will get now the square root of the R2 and R1. So the ratio here will determine, with the square root of that one, the quality factor. For example, if you want the quality factor of, let's say, 4, and this should be then the square root of 16, so you can take this 16 times larger than the R1. The cutoff frequency here, which is the omega C, is related to that natural frequency and the quality factor, which is for the high-pass filter. And the resonant frequency again related to the natural frequency and the quality factors shown here. There's also the gain peaking, which is called MR, is given by this expression. Now you see here the omega C again, the cutoff frequency in radians per second, omega R resonant frequency, and this is the gain peaking at that resonant frequency. This is a scalar value, not a dB, so in order to convert this, you need to do the 20 log of that value. And these are very important equations to do the design. And these are only valid for Q is equal to or larger than 1 over the square root of 2. Okay. Let's see also in more detail the effect of the quality factor. This is a general shape of a second order high-pass filter which has peaking somewhere. And we see here the high frequency gain, which is 0 dB or 1. And we see also this maximum, which is happening at there. So it is also given here in the dBs because we do 20 log of that MR. And this distance is this MR we saw earlier in the formula, so this is now how we can calculate that. And the resonant frequency, because at that point we have the resonant frequency, which is then given by this expression. Again, the Q and the omega n is in the picture. And this is again only valid for Q is equal to or larger than 1 over the square root of 2. And the cutoff frequency here is also shown. It's always related to that baseline, which is in this case 0 dB. So you always go down by 3 dB or 3.01 dB if you do a little bit more accurate. Now if you look at some quality factors, let's say 0.701, that is actually this one, then if you substitute that here in this formula, you get exactly 1, which means that you have a gain peaking of 0 dB, which is in this case just 1. Now you have here the quality factor is 1, that means you have then a gain peaking which is this almost 1.15. So going up with the quality factor will increase your gain peaking, and that is also related to the sharpness of your filter. So if you have a more gain peaking, you will go much faster down, which is of course this selectivity factor, which is an important parameter in the filters. Of course it comes to a cost, because if you make it sharper, you will go also a little bit higher there. So it depends on how much you accept as the gain peaking. Now looking at some values here, again the quality factor table here, you see here 3 and actually 4 examples. The Q is here 0.701, is Q is 1, Q is 1.5 and Q is 2. So for Q is 2, again this is valid for this condition. You see for Q is the highest peaking. By the way, this is the gain in scalar, not in the dBs, just to make it more clear. And you see here actually the gain has a value here at this point is 2.0656, which is also what we see from the table. Now if you go down with your Q, you go up a little bit lower, and then also your selectivity factor will go down, so your sharpness here, looking at the red line, is lower. Now the black one here is the Q is 1, which has this value 1.1547. It is also lower, the sharpness here is lower than this one. Okay, let's go now to our design example and use this circuit, which is the buffered second order high pass filter. And we'll also calculate at the end also our resonant frequency for this circuit. And the specification for our design must be the 500 Hz, which is our cutoff frequency. The passband gain must be 1 or 0 dB, so that means the high frequency gain. And our gain peaking, in this case, MR is 14 dB, which is quite high. Okay, let's start with the calculations. First, we start with the gain peaking, which is the 14 dB. We convert that to the scalar value, which is then 10 to the power 14 over 20, which is approximately 5.01. Now we can use the formula of the MR, which is then 2Q squared over the square root of 4Q squared minus 1. You substitute here this MR, which is calculated, and then you solve this using a solver, and you get here a Q, which is then almost 5, which is then 4.9866. Now the quality factor formula, we know that is given by this expression. You see here again the square root of the product of the resistor R2 and the C2 and the capacitor resistor R1 and the capacitor C1. Now we can, of course, make the equation like Q, this much Q is then related to that expression, but we see here 4 unknowns. So it is, in this case, too much. Now we can now also go to the cutoff frequency formula, and we use that specification we have here, which is the 500 Hz. And that is then given by this expression. We see here that we know the cutoff frequency from the specification and also know the quality factor. So we can now calculate the omega n. Okay, let's do that. First, we designate this as equation number 1. We will see that shortly why we need that. And this will be then 2 pi times this FC, so 2 times 500. And you now do the square of this complete expression where you substitute for the Q this 4.9866. You see that here, here, and here. Now this is just a number in the denominator, so that will be then times this 1000 pi effectively, and it will be then omega n, which is in this case 4847 radians per second. Okay. The natural frequency formula for this circuit is given by this expression, 1 over the square root of the product of these 4 components. Now we know what we have from our cutoff frequency calculations, and again we see here this equation, which requires again 4 unknowns, so we cannot solve this right away. That means we need to do more. So let's designate also this equation number 2. But we can go for what we said, the equal capacitor method, so we can say C1 is equal to C2 and just select some arbitrary value, let's say 10 nanofarads, and define it as C. Then this equation will be then just 4.9866 is equal to square root of R2 over R1, that's shown here. And this will be then 4847 is equal to 1 over the R2 times R1 times R2 in the square root times c, because this will be then c squared in the square root. And we know what c is because that's what we have selected here, and it will be then 10 to the power minus 8, which is 10 nanofarads. Now if you look at these two equations, we have two equations and two unknowns, so that can be solved. And let's start by squaring the left hand side and the right hand side here. So we will square this, square that, then we'll get this. Now we see here the R2 is then this much times R1. Now this is almost 5 squared, so you get almost 25 here. So in this case, a little accurate 24.866 R1. So the R2 must be then almost 25 times larger than R1. That's actually what it says here. Now we know that there is a relationship between now the R1 and R2, so we can now use this equation here in order to get to one unknown in our equation. So let's do that. So we substitute here the R2 here using this expression. So we leave the R1 and we replace the R2 here by 24.866 times R1. And now you see in this expression that you have only one unknown, which is R1. Now you see here R1 times R1 in the square root, so it will be then R1 squared. So we can take out that from the square root. That's shown here. You leave, of course, the square root of the 24.886, or I mean 866 in your square root. This is, of course, just a number times the number here. And now we can now rewrite this, so you have R1 is equal to this expression. Now this will be then almost 4.1 or 4.137 kilo. So we know R1. Now, since we know R1 and we also know this formula, we can calculate R2 here, and that will be then this much, which is then 102.88 kilo. So almost 103 kilos. Okay, now we know, now every component, we have selected our capacitors and we have calculated our resistors R1 and R2. The final one, which is our calculation for the resonance frequency, which is then given by this expression. We know the natural frequency and the quality factor. Substitute here the values and you get here 4,896 radians per second. This is very close to the natural frequency, still not the exact same. But why is it very close? Because the quality factor here is going up. So in this case, we have a quality factor almost 5. Now, the larger this value, the closer the omega n and the omega r are equal to each other. Okay. Let's now see that in the simulation results, and also here we see the circuit in the SPICE simulations. You see here the C1 and C2, 10 nanofarads each, and with the R1 and the R2 we just calculated. Now this is the gain plot. We see the log scale frequency and here the gain. The high frequency gain is indeed 0 dB, so you see here as we wanted, so that's the K is 1. We see the cutoff frequency is at 500 Hz. Why? Because from this we have a gain peaking, will be shortly discussed, and then go down by minus, so go down by 3.01 dB. So this much gain happens at 500 Hz, which is exactly the definition of a cutoff frequency. Now, at this frequency we have a peaking of 14 dB. So our maximum gain is 14 dB. So we have our MR of 14 dB, which is as we wanted. And this resonant frequency we have calculated, which is actually this. So omega r is 4,896 radians per second. If you convert that to Hertz, using this by 2 pi, you get here 779.2 Hertz, which is very close to what we see in our simulations. This is really just to rounding off error, so it should be actually exact. So we see that we have met all the specifications and checked our calculations using the SPICE simulations. Alright, it was our example considering the active high-pass filter design using a buffered circuit configuration. We have developed our design equations from the transfer function and checked our result using the SPICE simulations. If you have any questions, please let me know and I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video.